It's a series of informative sessions which is done by the Mathematics Society of University of Monaco that brings academic and undergraduates into one place to introduce upcoming domains in mathematics. So, it is a great pleasure for me to introduce today's speaker who will be talking about mathematics behind AI. He graduated from the Department of Electronic and Telecommunication Engineering of University of Monaco. He is currently working as a software engineer at BPH 200 in Singapore and as a visiting instructor at ENTC department. Please welcome Mr. Sandushan.
Okay, can you hear me? Right. Okay. I think you guys know me beforehand, I think, in mathematics and I think real analysis or something that the thing nobody knows anything about it, right? If I didn't anything. So today I'm not going to talk about much into those equations, so because otherwise you will fall asleep and don't understand what I said. So today's talk is basically on artificial intelligence, basically the mathematics behind artificial intelligence. So before proceeding to the talk, is there any Tamil ones or are there any Tamil or anyone who's the most prevalent language other than Sinhala? Anyone? Please stand. Anyone or all are Sinhala? Okay. So anyway, I'm going to conduct the talk in English because in this kind of topic, if you do it Sinhala, it's otherwise it is better to do it in English because in Sinhala you don't know. Actually, I don't know most of the time. Okay, so is there anyone who tried in artificial intelligence before? Before proceeding to talk, I need to know whether anyone who tried with machine learning or deep learning or any other thing. Have you tried yourself? At least single project, right? A course here, a course or anything. Anyone? Okay. So then, is there a very couple of things who tried artificial intelligence or machine learning or whatever you call it, or deep learning or anything before? So can you have an answer? What is AI? What is artificial intelligence means? Is it like you build a machine that can think, or what is your intuition about artificial intelligence? Because it is getting too much hype today, right? Like you say ChatGPT or bot or whatever you call it. So there's a lot of things going on. People call it AI. AI is the future. So you all guys, right? I think most of you guys, if you haven't done the field preparation, first thing that question you ask me, I want to do AI. So what is the department I should go? So are they from 22 batch? So majority of them from 22 batch means you guys are the first question is I want to do AI. So before going to you want to do AI, you need to know what is AI. Anyone? Come on, man. I go start number. What is AI? Just say it. Training? Yeah, training computer to make decisions. Okay. So I have something like this. So if AI is like training machine to think or some other thing. What? Some answer coming to this area. Okay. So I'll give some look in the answer because it's not my answer either. So it is you have the definition is basically the highlighter thing. AI is known as the development of algorithms and computer programs that can learn from data, make predictions, and improve their performance over time. It means AI is a subject of computer programming or computer science where we do not explicitly program machines. It means we just show some example to the computers or machines and they learn the task over time. So that's actually the idea behind AI. And also the motivation behind AI is they can replace in some places the need of humans. For example, if you want human to make cancer diagnosis, or let's say let's say you are a doctor, right? So by hearing the symptoms, you need to write a prescription as a doctor. If there's a doctor, the doctor task is like asking our symptoms and carry out whatever the checks required and give us a prescription. But if you can make some system that can input the symptoms of the patient and give medicine, and it is basically we call AI or artificial intelligence or machine learning. But the prominent thing, the common misconception among a lot of guys, I think most probably 22 guys, you guys think machine can think, it is the AI is the future. But if you go into the depth of AI, you will understand that AI is nothing but mathematics. So that's how I think, and I think that's way you should think. Because currently AI is at like kind of hype, like it's kind of water bubble, but in some point of time that bubble is going to like blast or something. It means like hype is gone and then world is come back normal and people will understand the truth. It means it has some wonders, it can do wonders, but not in that way. It means you cannot teach machine to think, but it is kind of like mathematical thing. So AI is essentially what you need to understand is you don't need to program anything. It will learn on its own by showing some examples. So there are a couple of ways you can do it. One is supervised learning. It means you give what should be your input. It means you give set of images or set of examples with the ground truth values. Let's say you provide images of cats and let's say these are cats. And you provide images of dogs, you say these are dogs. So next time you provide an image of a cat or dog without saying it is a cat or dog, machine will be able to recognize cat or dog. So that's the point of AI. So, okay. So actually this answer is coming from ChatGPT. So I'm too lazy to type and I just write what is AI in ChatGPT and it gave me this lengthy answer. Okay. So what is we like to do in AI? So the people who wonder, let's say you have a computer or it can be any other device, your mobile phone, anything. And then you're gonna input, let's say, this image of a cat. These are taken from internet like cat and you give this to the computer. And then suddenly your machine will output, oh, this is a cat, right? So this is actually pretty much amazing. So that's why people got amazed by machine learning or artificial intelligence. Suddenly it can do recognition. People say, okay, we see a cat and we can recognize the cat, machine can do the same thing. The people will, like non-technical people will say, okay, the machine is learned to think. So sometimes there are the hypes around like ChatGPT is trying to love the users and they have some feelings, but sooner you're going to understand that's all like nothing but hype, right? So this is one other thing. And other thing is, let's say, some other example, let's say speech recognition. Let's say if your mobile phone, you say, hey Siri, it will pop up and say what I want to do. And if you have hey Google, suddenly you apply up and say what I want to do. And you say call my lab or something and it will call, right? So sometimes if you are very good brainer or like some kind of like a mastermind, then it will ask which lab. Yeah, because even AI can confuse. So it is like you say something and it will understand it. So now you guys wonder, right? So if you haven't tried AI before, at least a single project or single code, now you will try to wonder how the hell that machines can do this, right? Because we do these things, let's say we see a cat and we see a cat and we made our decision inside our brain. And if we hear something, we also decode it from our brain, because if we hear something in Hindi or Urdu or any other language, we don't understand. But if we hear something that we know, we will understand using our past knowledge and memories and so on. So then, if we need to replicate behavior, let's say we need our machine to recognize this cat as a cat. What is the first thing you should do? Let's say you have a small child, right? Let's say your love story in this university is going a long way and at the end of the day you have a baby, right? So then you want to teach your kid what is the cat is, right? So you need your baby to, when you see a cat, you say this is a cat. So what is the first step that you need to achieve or you need to make sure to do this? Let's say for the baby, let's say you have some very small child, you are Akas or Ayas or any other thing, right? If you haven't think that far, right? And because that's the nature most of the things, not go that far. So anyway, so what is the first thing that you need to make sure? Very simple question, right? You need a computer, or let's say some small kid. You need to teach what is a cat is to that kid. So what is the first thing that you need to make sure? I'm single. So faster, you know, they can have a anyway, so I think so what is the first step that you need to ensure?
Show them.
That's correct. Show them a cat. That's it. Because before you teach them what is a cat, you need to show them what is a cat, right? So if we need to teach a machine to do the same thing, what is the first thing that we need to do? Show them a cat. At least we need to understand how they can see a cat, right? Otherwise we cannot teach them, or we cannot improve their performance without knowing how they can do it. So do anyone know how computers or machines store the pictures or they read the images? Do anyone know? How? Huh? Yeah, with the color images. So basically, how pictures read images, like they, in most of the cases, it uses the RGB color scale. It means in each pixel, it stores 3 values from 0 to 255. It means 20 to 255 means, let's say color scale. Let's say, what is the, it means, I will show you the image first, so then I can explain. Let's say, you have this image. So each pixel, you have 3 values. One for red, one for green, and one for blue. It means the number represents how much of color contains in that pixel. Actually, if you, let's say you have 3 numbers between 0 to 255, it means 256. For you can take each of the 3 values can take 256 values. If you might get to the power of 3, it is I think around 2.6 billion colors. It is how you say 2.6 billion colors in an image. That's how you get, because you can represent the color combinations of that amount, 256 to the power of 3, basically. So each pixel represented by 3 numbers, and if you write it as a like matrix for each red, green, and blue, that stick them together, it will look like a block or like cube of numbers. You have height and width; those are equal to the image, and also you have depth, or let's say we could usually call it channels, and you have 3 of them. And sometimes you can represent in CMYK or any other color mechanism, but the thing is the same. It means we see a cat, but our machine sees this amount of like numeric cube. It's it. And audio, how machines store audios? Do anyone know? Is there any from 21 batch? What's your department? I do. So then you should know how machines store audios. Actually, audios is pretty much straightforward. It is stored like sequence of numbers. It means each point of time it will store what is the magnitude of your sound wave, or kind of like because your audio signal is kind of a wave, like voltage, right? Because if I'm speaking, what will happen is, according to my voice, some voltage is deviating inside this microphone, and it will go to the amplifier, and you can hear it there. So, in computers, audio is stored like the same way as the numbers. It will encode these 2 numbers and store it as an array. And typically, I think you heard about something called bitrate in your audio files. That higher the bitrate, higher the quality. Bitrate means how many bits that you allocate to represent each number. If you have higher bitrate, means you can have lot of levels. If you are lower bitrate, you have lower levels. That's why, let's say you prefer like 320 kilobits per second. You have higher quality of audio clips. Otherwise, if you choose 128 kilobits per second, your quality is low. So anyway, these again are numbers. If you take text, how text is going to score? Again, these are numbers. You heard about STL encoding. All are the numbers. So my point is now you're going to make sense. Whatever you input to a machine, it cannot see images or hear audios or read text as humans. At the end of the day, it ends in some sort of numbers. It means whatever operation you do on these inputs should be mathematical. Right? It kind of inputting in mathematics. That's the idea behind. Actually, that's one motivation example to do the AI. So then, you know how machines see the inputs. Now we're going to see how we can transform these inputs into a usable thing. Let's say this is a cat, or let's say if you say I want to call my Baba and machine need to understand it, and machine need to understand what you say. So how is going to do that? Okay. Let's say very simple example. You need to input a number to your machine and you need to output whether it's even or odd. What should you do? Very basic example, right? What should you do? Basically, you run some programming script, right? So basically, that's what you do, right? You just take it and you just find out what is the remainder when the number is divided by 2. If it is 0, you call it is even, otherwise you call it odd. So, then the problem arises, right? Why can't we do that the same thing, right? Do the same thing to an image or audio file? Let's say you present the input of a cat, right? The cube of numbers. Why can't you do such a thing? By inspecting those numbers to tell this is a cat or not. What is the catch behind it? What is the problem? MIT? Yeah, it is different, right? Of course it is different. But what is the main thing restricting us to do it? Why can't you write just a for loop for a condition to identify it as a cat or not? So let me ask you this way. I asked a question like how you decide an even number or odd number, right? And if I give you a number and I ask whether this is a prime or not, is this straightforward than this? Figure out this number of prime or not, you have to write another bit of for loop and some sort of complexity is there. But now when we consider that, of course you can write a conventional program to decide whether this is a cat or not. Of course that can be do, but the thing is, it is highly complex. It means sometimes you may require 1 million programming lines, we don't know, because you have to write hundreds of for loops, sometimes millions of for loops and millions of if conditions, and then you can tell this is a cat or not. The problem is, in conventional programming, it is too complex or almost impossible. It means you cannot figure out what should we do, because to decide a number even or not we know, we have to divide it by 2 and get the remainder. But for image, what should we do? It is not straightforward answer, right? So that's why we think of it as in a mathematical approach. It means now we input this image to a machine and okay, we say you need to output 1 if this is a cat, 0 if this is not a cat. That's a very basic example. I just take the words out and deal with only numbers, because your image you can convert into the numbers, and the output I will also convert to two numbers. If you output, it will output 1 if this is a cat, 0 if this is not a cat. So then we denote this as x and I make it bold because it is a vector, or it is not a single number, right? It is a kind of vector. You can, it is a 3-dimensional vector because you can index. It has 3 index, to 1 to height, 1 to width, and 1 to the channel dimension. Or just you can, if you don't familiar with if this is a vector, you can think of it as a collection of lot of numbers, and such a collection of lot of numbers you can think of it as a mathematical object of vector. And I call this output is y. So our goal is, our problem is in AI, the problem we're dealing with, can we find a mathematical function which map this x to y? And now you guys will think, okay, what the hell this guy is talking about? These are very complex, right? This is not a simple thing. So don't worry, I don't use this example as it is to explain how we can construct this function. At the end of the day, you will understand You know y equals mx plus c, the equation of a straight line. Okay. And do you know how to take a maximum out of two numbers? Okay. If you know those two things, you can even build a very sophisticated machine learning system running today from scratch without using any library. That's how simple it is. So don't worry, I will guide you step by step. I just give you some introduction why we need to do this, right? So our objective is find some mathematical function, find some fx that can map this x to this y, right? So, okay. Now there are few people are there who do machine learning before. Have you ever think of like AI in this sense, or you guys have some expert on this kind of thing? I see some people there. You guys know how machine learning models like do something, how construct that kind of a function, or like you do get some model from GitHub and install code and just run loss.backward and optimize the state. That's it. Do anyone have studies in the mathematics like machine learning before? Yeah, you know some great. I will share some interesting information because in last year actually I engaged with some research in that optimization area also, like a mathematical thing. Okay. Now, very simple example. Let's look at the pictures. We need to learn some relation between two x and y pairs to our computer without telling what the relation is. So by looking at this example, if you see, these are my input values and these are my output values. So I need to give some input value to my computer and predict what will be the corresponding y value pair for an arbitrary number. For that I give this kind of black dots to the computer. Let's say these are my example. This will be your input output relation looks like. These are some counter examples. Figure out the example for me. By looking at this, I can draw this black line, right? It is a straight line because if you draw this a straight line, you can reasonably approximate the relation as a straight line, like linear relationship. So for this example, you call this such example as a data set, and you can approximate your y-axis as ax plus b, right? Some a or b. Now the problem arises, how to find this a and how to find this b, right? Because how many straight lines in a Cartesian space can you have? How much? Infinity number of times. So around this infinite number of straight lines, what should be my straight line correctly representing this straight line? The straight line I need. How do I find it? Any idea? Have you anyone in semester 2? I think you guys have already heard it. So what should we do? We can formulate a mathematical problem. So we're going to formulate this function. Yi is my, like the example that I need to predict, and my approximation is axy plus b. I just negate it. So if I square it and if I minimize the sum, what would happen is, by resulting a's and b's, if you plug into this equation, the error between those two is going to be minimal. This we call least square approximation. So how to do is, you differentiate this sum with respect to a and b separately, and each of them you equate them to 0. Because it can be shown that there should be a unique solution, because for this is a very simple example. If you do this properly, you can end up with these two equations. It means you just differentiate means you just take 2 out and this guy, and if you differentiate the inner term by a, it will result xi, the multiplication of xi. If you differentiate by minus b, it is 2 times this guy times minus 1, because if you differentiate this guy by b, it should be minus 1. Then you equate them separately to 0, you will end up with these two equations. If you solve this separately, you can get a and b. Very simple example. Mathematically you can solve. But what is the problem with this? Now you can solve it, right? Because usually this is called linear regression. You will learn in 4th or 5th or semester, sometimes even in 3rd semester. But what is the problem with this? Can anyone see a catch here? Anyone? First thing is, it is only taken out to one variable, that's obvious. The other thing is, what should happen? Okay, what should happen? This is a very basic example, right? I give one number and I want to predict one number. What will happen? My output relation is look like this. Can you guess the function? Approximation to that. It's not a sine, it's not a cosine, it's not a tan, it's not even e to the power x. How are you going to build a function model for this? Anyone? Oh, I am going too fast. You cannot grasp. Because it is a problem with me, I am talking too fast. If that is the case, please sort of some signal even to the organizers, I don't mind. Say, I have this sort of, because sometimes I move too fast. I forgot to mention it earlier. So, how are you going to model this? Let's say you want to approximate these your like data set or some example that you want to model, and you need to approximate it by some form of function fx. Is it a plus b? This should be engaging, right? Otherwise, this will become a typical talk or a lecture. You guys listen and you will sleep and you will go out and you will learn nothing. So, will a plus b work? Here. Just take my mouse out so then I can come to the middle. Okay. So, now I come to the middle, otherwise middle guys will sleep. Okay. Will ax plus b work? The linear model? Sin x divided by x, tan x, tan inverse x. Nothing will work, right? Okay. So, the equivalent mathematical problem is we need to find some fx to minimize, let's say, some loss function. Loss function is nothing but LV is like some function which measures the distance between your prediction and actual value. Let's say you can take the difference between them and square it, or otherwise you can take the absolute value, you can do anything. It should be a measure how much your prediction deviates from the actual value. At the end of the day, if you minimize that, your predictions and the actual value should cross together. That's the whole point of it. For this example, you can just take the difference and square it, or otherwise you can take the absolute value, that nothing wrong about it. The only thing is it should measure how much your prediction differs from actual output. Okay. So the problem is, one thing is we cannot model the function fx. It means we don't know how our function will look like. It means actually we don't know even the shape, right? We don't know what is the component inside it, how much it look like. We don't know. We don't have a clue. And another thing is, for this optimization problem, we don't have an optimal cross-form solution. It means we, as an equation, we cannot see what is our optimal solution is. Okay, solution is actually use the technique called gradient descent, which I am going to explain next to you guys. And the solving this to not have a cross-form solution, we can get a gradient descent. That's no problem. And how to model function fx? It's the idea behind machine learning, right? So that's the actually breakthrough coming when you, because there's no point of having gradient descent without having a function to model like any arbitrary complex relationship between two variables or two inputs or output relationship. If you can't model them, you cannot optimize it. Doctor's algorithm is gradient descent. It is something like this. So, optimization problem is something like this. Let's say you have a loss function and you can write it as some parameter with respect to w or something. Because here your xi is our example and yi are our examples. You don't need to change about it. What you're going to change is this fx. Let's say any changes in w, so any changes in f can be representing w, and you can write it as a function of some variable w. In our simple example, we have h plus b. We can write that loss term that we define, the difference between the square with respect to a and b. Think of it as a w which defines this function. So if we can define our function with respect to w or some variable, this loss became a function of w, because we don't need to change xi or y. It's how you do in assignments, right? If you some lecturer gives you to put some data set, what you change the data set and fit. It's not applicable here. We need to set our data set by changing this function. So our equivalent mathematical problem is to find some let me check. I have got this. Seems like okay. So idea is gradient descent is something like this. Let's say ideally you would need to be here with respect to W. Let's consider W is a single variable, not 2 or 3 variables. You need to be here. So can you say what is the value of this gradient if W is somewhere here? That's the sign, whether it's a positive or negative one, if you get the slope of this function over here. Huh? Positive or negative? Positive. Yeah. Positive. So then, it means, now I ask the question, okay, gradient is positive here. Do I need to increase or decrease this W to get here? Increase or decrease? Decrease. If the gradient is positive, I need to decrease. Let's assume W is over here. Now, what is my gradient? The sign of the gradient over here, negative. Do I need to increase or decrease my W to get to the optimal point? Increase. It means, if my gradient is positive, I need to reduce it. Negative, I need to increase it. It means, this is the gradient descent algorithm. Do the exactly same thing. You initialize W to some initial value. It can be 0 or anywhere. And then, you calculate the gradient at that point. Let's say some arbitrary Wk at some k iteration, you have some Wk over here. And you calculate the gradient. If the gradient is positive, you reduce some portion of the gradient from your variables. It means I am here, I say, okay, your gradient is positive, you should be go here. And I say, if you here, okay, your gradient is negative, once you take this minus sign, okay, the algorithm says you need to add something to your value. And it will go in this way. And this gamma guy over here, we call it gradient descent. Sorry, the learning rate or step size. It is changed usually interchangeably, or in machine learning context we usually call it learning rate. But this is the very basic gradient descent algorithm. There are several other algorithms, ADAM or ADMM, RMS, lot of things, but this is the basic idea over here. So then, this gamma is called a step size. You can optimize it using this algorithm. So what should be the gradient in this point? This simple like this very curvaceous function, 0. But in real complex functions you don't find this kind of nice shapes, and we call it usually convex function, but you cannot find convexity. Usually most of the objective are unconvex, and you cannot sometimes even find like this looking nice and differentiable functions. Sometimes you need to approximate to a derivative, so that is like some complexity and out of the scope of this talk. The idea behind it, you can optimize any given function if you can find some derivative of it using this gradient descent algorithm. You can converge to a global solution if it is convex to Alaki, or even you can convert to some local point. It means minimum point with respect to some sort of neighborhood. Okay. Now if you are sleeping, wake up please, right? So all of the things I'm talking here before, I think you may heard, or you may feel like very simple things. This is very simple, but I think most of the guys don't think this is a very simple or powerful idea. Let's see how we can unleash the power of gradient descent into the AI, or how we can give the power to the machines that can approximate literally any relation between input to output. I take this very simple function. I take some two real numbers A1 and B1, and I take A1 next plus B1 and take the maximum out of 0 and that value. If you see, if you go over here, right, the function value is positive, so it is a straight line. When it starts to go negative, it will set back this value to 0. This thing actually we call it ReLU activation in AI context. For now, forget about ReLU activation, just think of it as you calculate some linear thing and get the maximum out of it. And I take a couple of these functions, right? And this one and this one, same as same. You can just easily compute like your computer too. You can compute some values and just take maximum out of 0 and that value in that time. And then, if you add these two, I do nothing, right? I just calculate those three functions and just add them together. What will happen? Can you say, what is this shape look like? What does the shape look like? Any like familiar shape? Anyone? You guys are asleep. If Sri Lanka has to face war again, there is going to be disaster. Right? Retired soldiers have to come and go to the war. The young generation is look at this. No, right? Because Morocco is like place where many boys and less girls. If you want to win the race, you need to be active. I test it. So, anyway, so what does this function look like? It's a mass society, right? What is? Huh? What? Yeah, function okay, but if you only consider shape, like, what does this look like? X square. Right? So how nice it is, right? You have 6 parameters and you just add them together. It is approximate x square, right? Like x square. At least it look like x square, right? So if you want to try them out, these are values I use, and you can write a simple Python program and see. And will this actually work, right? Don't take this for granted, right? Will this idea be actually work? And I'm going to build my first AI model with these kind of very simple relations. Right? Will this work? Hands up, let's say this can successfully approximate x squared function at least. Anyone? Using only these two operations. Beginning of the talk, I told you, right? Ax plus b and taking the maximum of two numbers. You can approximate anything. I give you the answer. But now I ask, do you convince yourself these two operations can do anything, can approximate anything? Or it is too simple for you guys? Do you ever think about that? Right? Okay. At least like you see something this can do, right? Okay, go to the next slide, I will show you. So these are the functions I take, right? And okay, this is my function. And now if you take the function, your W become this A1, B1, A2, B2, A3, B3. Because once you take this loss function, this fxi y1, what will happen? This fxi is in terms of these 6 parameters. Understand? Anyone else know about it or any clarification about it? Anyone? No, right? So then I can perform this gradient descent algorithm, and what will happen is exactly only using these 3 functions I was able to approximate x squared function to a like kind of like to that approximation, right? Not pretty much do better job, but it will somehow approximate. Now my question is, now you guys say, okay, these guys take 3 functions and perform gradient descent or something, and if you don't know what is gradient descent is, these guys perform something and get this thing. Whether it is impressive, you say it is not impressive because there are a lot of see, this is not equal to this. See, these are 2 different stuff, but not much approximating correctly. You guys say this, right? And can someone say how I can improve the approximation if I want to? At least like give some answer, right? It can be wrong or it can be correct. Doesn't matter, it is worth trying. That's how machine learning works. People have tried different ways and finally found it very simple thing, do the thing. And irony is, to figure out this, people will take, I think, around 200 years after the invention of calculus. So that's a sad story. And it will take another 200 years to implement this in the computer. To figure out how to implement this in computer hardware much more effective. That's the idea is actually in media. That's they actually bring this to the modern world, but that's why I will explain a bit of this towards the end of this talk. But can we do this better? Any suggestion? This, again I remind this is a mathematics society. So one of the top ranks in the country, so you need to understand. I think almost everyone got 3 A's, right? At least 2 A's and 1 B, one A and double B. So anyone? Huh? Yeah, we can increase number of functions. Okay, let's say what happens. I take my one function look like this, and my approximation look like this, and I'm going to increase n, right? In 3, I will look like the same result. If 10, somewhat good, but not that good. But 100, boom. Right? 1000, almost like overlapping each other. So what's the beauty of this? Now one can argue. Now you see that this is doing something, right? But what is the most impressive thing about it? This is not like a magic, right? You go, wow, okay, this guy good, this guy good. Not like this. What is the impressive thing about these two functions? This is a very simple approximation. I just take some sort of function, I approximate y equal x square, right? Not a real world application. But what is the impressive thing here? Can anyone say? What is the thing that you surprise the most? In other words, you? Think I know. What is the thing you surprise the most? I take this kind of like addition of this simple functions in a linear part and take the maximum out of 2 numbers, and once it is optimization, I can approximate y equal x square. What is the surprising thing here? What is the promising thing? You feel that this can do some huge things. Huh? What? Big data. Not big data. Yeah, big data you can do. But what is the motivation? If you see this, what is like convince you that this can work in big data? This can use some complex tasks. What is the impressive thing about this? In previous example, when I with the line y equals ax plus b, I saw my result would be look like a straight line, and then I say y should be look like ax plus b. But here, do I give the model of this mathematical function that my resulting function will look like this shape? Do I have a single mention about the shape at the start? The algorithm figure out the parameters using gradient descent. That's not a big pretty much surprise, because once you get some sort of redox measure and you can optimize it. Impressive thing is, without mentioning this is a y equal x squared shape, algorithm is able to recognize this is a y equal x squared shape without even mentioning the model. It means by using, let's say here, let's say n equals 100 class, using 200 parameters, 100 a's and 100 b's, I am able to figure out how does my y equal x squared function look like. Okay. Now you guys say, okay, this is good and this is the machine learning and that's it. Is that the case? Of course, this is the only explanation, but how we do the thing is the difference. Okay. Now, what is the problem with this? Or how we can see the limitations of this? Because anything in the world comes with its own limitations. Okay. So before going into that thing, I need to tell you that how we perform this optimization. Now you are hardcore mathematics fan, and you can go see some what you call plumbing syntaxes. If you don't understand, don't worry. You can figure out later. Okay. So here is my function, and this is my approximation, and this is my loss, and I define LFXI by all these losses for a difference and square. So, can you tell me, this all guys I assume combined advanced level mathematics. If I differentiate this guy by y I hat, what should be my result? Can you differentiate or not? With respect to y one hat, yi hat. Can you differentiate or not? Differentiation. Can you calculate the derivative of yi minus yi hat squared terms with respect to yi hat? Yes or no? Oh my god. Yes or no? Yes. If you calculate, it's a very simple problem. If you can don't remember it, just go back and do variables again. Or I don't know. So you can do sometimes find a job, right? Because you don't deserve to do the degree. Just again, right? Because it is a very basic thing. You can get a derivative, and if you differentiate this y hat with respect to any of these u's, your derivative will be 1 because it is just a summation, right? And if I take uj, any of the u's, it is look like this because if this guy is greater than 0, it is this one, otherwise it is 0. And if you differentiate it with respect to aj, if it is greater than 0, this is x, otherwise this is 0. And also, and using this guy and these two guys, and using the chain rule, if you multiply this guy, and this guy together, you will end up the derivative of this L with respect to A. Right? You can get this derivative. It is the chain rule, and you can do the same thing to your B as well. And you can calculate the derivative with respect to AJ's and BJ's with respect to these L's. Once you know that, because your loss is just the summation of this one, because again if you differentiate with this guy because it's just summation, your derivative with respect to G is nothing but the same derivative because it's just a summation, right? It's like if y equals A plus B, if your derivative y differentiate y with respect to A, it is 1, and with derivative y with respect to B, it is also 1. It's just summation, nothing but more than that. And then what will happen? You can have parameters like this, and you need to perform this gradient step. This step is reduced to this one. It means you take your AJ, and you take a given k times slot, and you multiply by gamma and subtract this dabba LK over dabba J, the derivative we found in the previous step. And again, you can do this for the B as well. And the beautiful thing is, you can implement this whole thing with around, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 lines, right? 13 lines. This is actually how you can code this in a Python program. Once you do that, you can get the result I shown in the previous slide. This one, right? Okay. Now you know this actually. Do anyone need about this calculation? This I don't want to go into depth of this calculation, how to perform derivative, but only thing I need to show it. So you can calculate this dabba L over dabba y hat, this y hat over dabba uj, and this derivative by using the chain rule, you can get the derivative of these losses with respect to AJ's and BJ's using the chain rule. That part is understood or not? If anyone is there is not understood, not clear, I can explain it again. So I just have to press your hand. Otherwise you will fall asleep. Okay. So then, okay. Now, what is the limitation of this? So this is actually the total implementation. You have this training part and you have the estimation part, and this is actually the code of Python for training. I will share this code if you need. You can, when you are board in place or when you are at home or anything, you can try them out. I will. I think I have code with me now. I will upload to a drive and share with you the notebooks. And okay, now you can tell me what is the limitation of our simple function or our simple method. Now you can wonder, okay, is this the AI? So of course it is not simple as that, but what should be the limitation? Can anyone tell me? What? Yeah, that's one thing, function not being convex. That's one problem that we need to handle. The other thing is, what will happen, our function is too complex. and our model cannot represent it. I train it to train to approximate sin x function, and it will just give me a straight line, variable prediction, right? So, and then I tried some different approach, very simple modification, and instead of just taking the summation, when I take in this function, I introduce additional coefficients Cj's and some bias term D. Using this thing, let's say using n equal 50, I need to get some sort of this approximation, right? And using n equals 100, I use some sort of this approximation, but it is not perfect, but not terrible as the straight line, right? At least it try to see the approximate shape also. And if I use sin x over 2, like some kind of reduction in the complexity, this model will be able to represent your sin x function. But the catch here is, also you can train this model with n is 10 to let's say 1000 or 2000 or something else, then it is a very bigger model and very complex, and most of you will be able to approximate this function pretty much the same. But the thing is, you will require more time to carry out the computation, as well as you need to optimize your learning rate as much as possible, because there are something coming down like gradients exploding and other stuff. So when you, let's say you can think of this way, when you have a lot of parameters, let's say you have 10,000 parameters, you have a lot of search space. It means you only have correct one solution, but if you have many solutions, many incorrect solutions, then your search space will be large, right? When your search space becomes large, what would happen is your algorithm, the chance of it can go wrong, become very large, and the one who developed this algorithm need to do a lot of part to avoid that. Let's say you can easily make a choice when you have only 2 choices. But if you have 10,000 choices, how are you going to make a choice? It is very difficult, right? Even for a human. Let's say to moratorium it is not a problem, because you only have, anyway you have only 150 choices, if you understand correctly what I mean, right? Maximum 200 if you are lucky enough, but most probably it will be around 150. In our case it is 159 for the boys. But girls, the harder problem is there, because they have around 750 choices. So anyway, so then there is a that looks like that. So okay, now I make this like power of depth. The thing is, if I use this function, even from sin x divided by 2, it will just use this straight line, right? Very terrible prediction. But if we use this, introduce this additional term, this coefficient and the bias term, using n equals 20, I can give some sort of good approximation, right? You can see this guy, this approximation is somewhat good. It means this guy using around 200 parameters. If we count this parameters in this one, it's around 61. It means using 50% or that less than half of the parameters used here, it can perform better. And can we do better than that? Can we do better or not? Anyone? I chose the answer by mistake. We can do using neural network. If you use a neural network, you can approximate very precisely, and loss will be very low. Okay, so what is a neural network? Do anyone know what is a neural network? What is it?
It is a kind of a program that relates to neurons.
Yeah, neurons. So, but there are neurons in the body as well, right? So why did it get the name neural at first place?
It contains many layers.
No. Yeah, it contains many layers. That's correct, because as if you say our neural body or our nerve system, it will contain millions of cells. If you want to carry out a message from my hand to my brain, it will involve like around million cells. Convert message from cell to cell. So that kind of thing using neural networks. Neural network is consist of these kind of layers. The way its name is, it will look like this. It has many inputs. You can give it to many real numbers at this inputs. So what this neuron does is, it takes the weighted summation. It multiply each number with some weight or some other real number which is a configurable one, and add some bias. And then take maximum out of 0 of that summation. This maximum is actually usually called the relative activation. You can use other activation as well. But for simplicity, throughout the talk I will use this maximum. Taking the max between 0 and this one. Right? You can take any of these methods which we call as activations. That the purpose of this introducing this maximum term out there is to introduce some non-derivatives. Assume that you don't have this maximum over here. What will happen is, no matter you use how many neurons, it will become a linear function at the end of it. Right? Because if you take this output to another neuron and you take the summation like this, what will happen? It is just a linear function, right? Nothing but a linear function. To give the power to estimate the non-linear relations, you need to introduce something like this. Either max or some other type of some other non-linear thing into these functions. Okay. So, and by simple calculations, you can easily calculate this derivative as well, because once you have this function, as we did previously, we can calculate the derivative of this y with respect to xi's and with respect to weights or this bi's or ai's. Any of these terms you can easily calculate. Is this part understood or not? Is this part understood or not? You can calculate these derivations. Right? It is not a big deal. So neural network is you calculate many of these layers together to perform this giant network. It means you give input here to give all of these neurons, and these outputs give all of these outputs give this neuron and this neuron and this neuron, and each of them has different weights to each other. And at the end of the day, it will output some output to our network, and using gradient descent, we can tune the weights with each of these lines to get our desired output. This is actually nothing but the extension of the idea we discussed here. This idea, right? Instead we use only one summation. Here we have lot of weighted summations. And okay, then how are we going to implement it? Previously using NumPy, and I include all together in 13 lines. But the thing is, if you're going to implement this kind of thing by hand, it will take you around 1 year. Just to code the how to calculate the output and the derivation and the optimization part by hand, it will take around 1 year, and it is a very terrible task. I see some guys falling asleep. So I know you have a very long day. Luckily, we have some sort of open source or very free to use libraries like Torch, TensorFlow, some Handle. There are a lot of libraries which can do all the hard things for you. Only thing you need to do is just define the model and write this scaling loop, right? I just include this here because I know you guys this easy equation, and see you guys who are very lazy, because I don't like to implement the same thing again and again. But there are libraries always do this for you, and you can easily implement this using existing Python library. And then, what is the power of these neural networks? Can anyone tell? Will this kind of thing work? If you do this kind of thing, what will happen? What will happen? If you do this kind of thing, not only sine function, very different functions, you will be able to approximate to pinpoint that use. If you go over here, you can approximate sine function. This is we call sin function, sin x over x, and this is some random function I take by addition of 10 sine functions using different frequencies. And this is also some other thing, I take some other random functions and I generate using addition of some different sine functions. But each of the time, my neural network, I think it is around only 200 parameters or so, and it will able to output approximate this function. How can I see? It's only around contain, I think 200 neurons, right? Only 200 neurons, but it will be able to output this function. So now, using the simple function, by implementing it slightly different way, it means not only just taking the summation or weighted summation, by stacking this up, the same operation again and again,
we are able to represent any arbitrary complex function using some set of non-parameterization. The power of this thing is, in each of these cases, we don't need to provide the shape of the function to our neural network. This network, this function, and this function, this function, this function, this function, all are approximating using same neural network or same function. That is what using Python, right? It's again a mathematical function. The beauty of this is, once you define your network, it can figure out many different complex relations without even mention about the shape. You don't even tell that this is a mention of tensile function. If you given any arbitrary function, it will give you the approximation to a pinpoint accuracy. Okay. So what will happen if you have more inputs or more outputs? Let's say you want to input the image or you need to input a sound clip. No problem. Just you have to take this input. In input you have to take some more inputs and all of the operations are the same. And also you can have more outputs as well. Instead of outputting one number, you can output many of the numbers as you need. But the only thing is, each of these neurons, the only operation carried out is the linear operation, the weighted summation and the addition of the bias term and taking the maximum order. If you choose the reductive activation. For simplicity, just go with this taking maximum out of 0 and this one. And now the thing is, as mathematics, so now you see how simple mathematics can unleash the power of representing these complex functions. How we can optimize this? Let's say our neural network like this, one neuron. You have many inputs and your output can be fed into many neurons. And then you can represent your y as this, and then you can easily calculate these derivatives very easily. It's pretty much straightforward. You can calculate derivative with respect to b, and derivative with respect to wy, and derivative with respect to xi. You can calculate here. And also assume you have the derivatives with respect to your loss in this neuron, and this neuron, and this neuron, and this neuron with respect to its input. Because if you fed the same output to different neurons, each of the neuron will have a different way of looking at this gradient. So that is one challenge that we are going to, some confusion point when you are running into if you going to write backpropagation algorithms by yourself. But it turned out that you can use this DABA L or your change of your loss with respect to change of input to these neurons in this way. If you do perform what you call the partial derivation or the partial derivation, I think in fluid mechanics you do in the first semester, you can write the summation as this, your DABA L. And also I replace this DABA I term with DABA Y because these are all same. I just use this notation yi to yin to denote that the same output going to be fetched different parts. And then you can calculate DABA L over DABA Y with respect to this output using this equation. So you don't have to pretty much go into depth on these mathematics now, but the only thing you have to figure out is we can calculate each of these derivatives based on the previous outputs. Once you do that, you can calculate DABA L over DABA W by using the chain rule. It means using this guy and this guy, you can calculate this guy. You will just the chain rule. Once you multiply these together, DABA Y cancels out. It's act like that, and you can calculate this guy. And if you multiply this guy and this guy, you will get this one. Or if you multiply by this guy, you will get this derivative. It means you can calculate your derivative of the loss with respect to inputs, with respect to weight, and with this bias term using the chain rule. This is called nothing but your strange backpropagation. Right? Backpropagation is nothing but once you have the derivative of one layer, using chain rule, you can calculate the old derivative of the previous layer. Because when you calculate the input, output, you give input and you go in this way to the output. The backpropagation gain its name is you start calculating derivative at the end point, your output, with the derivative with respect to the loss, and then you come forward to the previous layers. That's why it calls backpropagation. You start from the back and come to the front. So that's how it's going to be implemented. So now this is your neural network. That's a very complex neural network. Using backpropagation, this is the same function implementing all of the neurons here. You can calculate the derivative of your loss with respect to these weights using backpropagation pretty much easy. Once you do that one, you can perform the optimization procedure using the gradient descent pretty much easily on each of these weights and these bias terms. And when you perform sufficient number of iterations, you can get a good accuracy on your task. Okay. Now some will wonder, let's say, now back to the previous problem. Now you know how can build a complex neural network and optimize it to output the result we want. But now the problem remains, right? Let's say we need to input a picture and we need to output whether it's 0 or 1, telling that this is a cat or this is not a cat. How can we do that? Previously we approximated sine function or any arbitrary function, but they are not like this, right? We are approximating some continuous functions. But how are we going to make the machine to output exactly 1 or 0? At least a value between 0 and 1. How can we do that? Anyone? Anyone know the machine learning classifications before? Can you remember something that you used in the last layer to achieve that task? Anyone? Okay. So I denote this output x and I will denote this output as 1. And what the problem is, how we going to get 0 and output? So it is very hard because you cannot train the machine to exactly output 0 or exactly output 1. It's pretty much hard, right? If you try that out, you will almost figure out nothing. So what we're going to do is, we're going to input our image or any other input, very complex input, and we let output some z value. It's a continuous any different value. And then we need to use something called sigmoid function. This actually, if you plug into any value, this will map your output into a value between 0 and 1. Because if you put very smaller number here, let's say this is going to minus infinity, this thing will go to 0. And if your z is going to positive infinity, this output will go to 1. If you plug in any real number to this z, this thing will remain between 0 and 1. And then once you restrict that value into a range of 0 and 1, you can assign it 1 if it is greater than 0.5, or assign 0 if it is less than 0.5. And the beauty of this thing is, you can differentiate this thing. So you can differentiate these two. If you differentiate it with respect to your z, you will get this thing. Not only that, you can have different sort of mathematical functions in activations in machine learning context to do the same thing. It means the standard function is something like you get to the power e to the power z and minus e to the power minus z and divide it by the summation of those two terms. And the standard function restrict your output to in between -1 and 1. Let's say if you want something to output -1 and you have to output some direction or some sort of score something between -1 and 1, and you can use standard function. And for some classification problem, you can use softmax. Let's say you output some vector and you need to find out what is the most likelihood class. So then you perform softmax. It will convert your output vector to a numbers between 0 and 1, and it is have one other property. If you add those numbers, it will result 1. It means you can map any vector of real numbers which is one-dimensional to a probability arrays using this softmax function. Okay. Now, I think I talk a lot, and this is our final neural network look like. You have some x and you have some y hat as approximation, and you have some function inside your machine which is defined by some set of parameters w. So our goal is finding the optimum set of parameters that w which can map this x to f, right? So in doing that, you need to define first. When you define a machine learning model, any machine learning model, in a mathematics perspective or as a practitioner, first thing you need to do is identify the suitable loss function. It means if you're going to approximate a function, your loss function would be the difference between the true value and the approximation, and you get square. But if it is a classification problem, you need to identify what is the suitable loss function is. Usually we use something called cost entropy loss. It is actually the difference between the probability distributions to deviate between your probability distribution and your ideal probability distribution. Or sometimes you have focal loss, so segmentation task. So first thing, if you're going to do machine learning in any domain, it can be natural language processing or image processing or audio or text recognition or any other task or function approximation. First thing you need to figure out is what is your loss function, because this is the loss function that you need to minimize during training. If you choose wrong loss function, it will give a very low value to your loss function, but will deliver out because you haven't chosen the loss function correctly. The second step is you need to perform backpropagation to find the one parameter. So once you figure out the loss function, you can do easily that. And then you can perform gradient descent to optimize the backpropagation. So the main motivation. So now I explained about how the simple functions can be used to approximate many complex relations, and even a simple example, the function approximation, it will do an amazing job. So the important thing is that I need to convey throughout this talk before going to the next part. To this point, I already discussed the very simple basic mathematics behind. Sometimes you feel like, oh, this is the AI. Is that very simple? This thing is very simple. Very simple mathematics inside out there. But the problem is, people are going to try this AI without knowing what is actually going on inside. You can use torch, tensor, anything without knowing this mathematics. You can use AI to any application. But the problem is, you cannot optimize. Let's say you need to perform image recognition tasks and you perform the biggest network available in the internet. But what will happen is, you can perform the task, but you will waste a lot of resources. So if you need to actually become a good researcher or actually become a good engineer, you need to have this inside mathematics. Otherwise, you will do some sort of like Mason pass on the head machine learning. That's actually my supervisor used to told me when I do my final year research on the gradient descent. Actually, it is apparently going to be a gradient descent algorithm, but I will show it to you after that. If I have that paper in my laptop, I show it to work. And there's something called also minimized gradient descent. I will explain it briefly. Let's assume together throughout this talk I explained calculating gradient with respect to only one example. But what will happen if you have thousands of examples? You need to calculate the loss of each of these examples and get the derivative and average them. Because let's say you have 10,000 images, you don't need to train your network only on one image, right? You need to train on all the 10,000 images. If you have 1 million images, your model need to perform on all 1 million images as the same. If your training set is that one. So in that case, what will happen is, calculating this loss function is pretty much expensive, because you need to run every image to your model and calculate derivative with respect to each image, loss of each image. So what is the technique behind over here? So in practice, what we do is, let's say we have 10,000 images, we say, okay, we only pass 100 images to our model and we calculate loss with respect to those 100 images. And then we calculate the gradients and perform our gradient descent step only using those gradients calculated with respect to those 100 images. That thing we call actually minimal gradient descent. It is nothing but same gradient descent algorithm, but only difference is you don't consider the whole data set, consider only a portion of it. And also in machine learning context or any context, this is also called stochastic gradient descent when b equals to 1. It means if you consider only one image or one example per time, you call it the stochastic gradient descent. But if you properly go through mathematical optimization literature, the stochastic gradient descent has wider meaning than that. It is stochastic gradient descent means you approximate the gradient with some error. It means you cannot calculate the gradient, let's say this gradient approximated correctly with the spiral descent, but instead you have some sort of error, epsilon or something to approximate. So that's what you call stochastic gradient descent, but it is not much you need to implement gradient descent algorithm because it is handled inside the libraries. But if you like to engage in mathematical optimization, then this thing will come handy. Okay. Now, so in neural networks, we have several set of layers. Basically, we have linear layers. It means like the Ax plus B type of layer. There are a couple of layers, let's say convolution layers, fully connected layers, or usually called dense layers, and many of these linear layers. These are the main layers that we have weights that we need to optimize. And also we have some pooling layers, let's say average pooling or max pooling. It is nothing but you can think of it as a function. You have several type of numbers, you take the average of them, or you take the maximum out of them. And also you have some sort of activation like ReLU, SILU, softmax, sigmoid, tan, and a lot of bunch of activations. The important thing to note is, these things are the only one contained unified parameters. These two guys are the ones which introduce nonlinearity onto our machine learning models or our neural networks. And also you have different loss functions to certain different approximations. Let's say MSE loss, this is the one we use to approximate function, let's say mean square. It means you take the difference between your model output and your true output or your expected output and you square it and you average it over training examples. And also you have something called cross entropy loss. If you learn about communication, you will learn it later in the semesters. It is basically you measure in between. It is cross entropy loss means the measurement between two probability distributions. It means usually in classification class you should have 1 0 0 0 like probability distribution. It means correct class it should output probability of 1, other class it should be 0. But in machine learning output you will around, let's say correct class you will get 0.8 and other class let's say 0.01, 0.03, 0.05 and so forth. So in that case you measure how much is different from expected distribution versus the actual distribution. Now you are predicted output. And also you have a lot of frameworks like NumPy, Torch, PyTorch, TensorFlow, Paddle to implement neural networks by your choice. So you can use any of these to implement. And now comes the interesting part, career paths. Since you are all together, I think most of them are yet to choose your department. Here are the career paths that you can choose in machine learning. So I will talk a bit on this rather than going into pretty much details, but there are two things that you can do as a machine learning engineer. One thing, you can become a researcher. Another thing, you can become a machine learning engineer. There are always two types of research that you can do. Empirical research means that is the most widely doing thing in the industry, even in the world as well as in Sri Lanka or anywhere. Empirical research means you are given some application and you build some machine learning model and you do things experimentally. It means you build a model and you train it and you see accuracy is improved or not. If it is not working, you do some changes and run the experiments again. This kind of experimental thing that you can do in your machine learning research most of the time. Most of the components will result in experimental stage. It means you don't need to go much depth into mathematical proofs. That's one. The other thing is theoretical research. In theoretical research, you don't need much worried about experimental unless you need to validate your theoretical proofs. If you like very passionate about mathematics or optimizations of research, you need to like write out the derivations and prove theories for yourself. You should focus on theoretical research. In that case, you need to be pretty much confident on the mathematics on like calculus and the linear algebra, and I will explain that to next. And also there are two career paths that you can take is ML Ops engineers and ML Dev engineers as well. ML Ops and ML Dev are let's say ML dev, there are two types of research. One guy is developing machine learning models. Let's say they test it and they deploy the machine learning models to some research and development phase. Let's say you need to develop something to detect face recognition attendance system. They are the one who develop the machine learning model and test it with different images and gain some values. And ML ops engineers are the one who take those machine learning models into the real world. It means you cannot implement a machine learning model in real world inside a Jupyter notebook. You need to get to the real world and you need to implement it in a cloud or somewhere else, and you need to handle the practical difficulties when it run in the real time or real world. So that is one kind of path that you can take. So, and you can search about more in this, but in most of the time in industry, if you go in industry, most of the time you have to do empirical research and these ML and ML engineers. The theoretical research, more probably, you will find in academia. If you go into higher studies or PhD or a master's or MPhil, you can find out that one. And these are two different architectures. Now we are also talking about, let's say, inputting numbers and vectors to a neural network. So what will happen if you need to input an image? Let's say image, you know, you have three channels and it's a cube of numbers, and you need to give this input and output some sort of values. So here there are something called convolution neural networks. Convolution is nothing but you implement this same as the linear layers, but you only consider some neighborhood of an image. Let's say you only consider 3 by 3 square of your image and only take the linear output of this block, and then you move that square a bit and take that output. And that case, you call it a CNN, and CNNs are very powerful to detect image recognition tasks as, let's say, image classification or image segmentation. You can find out in more if you explore in internet or any other thing. Another thing is we have something called recurrent neural networks. Recurrent neural networks is something, let's say you need to analyze audios. Let's say you need to build some system to understand voice commands. Let's say you say, let's say, I went home, this is your sentence. And if you need to get the meaning of that sentence correctly, you need to get the order of the words, and if you consider word, you need to get what is the word before it and what is the word after it. So that thing that you can do with recurrent neural networks. There are a lot of architectures. So, but no matter what is the architecture, no matter how fancy you draw it, the only operations inside these things are the linear operations I showed you before, and then non-linear activities and the backpropagation. That's the only three things inside these neural networks which gave this power. So I choose this very simple example to illustrate how we can build a neural network from a very simple example, because if you are new to AI, don't go straight into CNN, go straight into RNN. Try to build very simple thing first. It doesn't mean that you always need to hardcode the algorithm from scratch. At least that initial phase, your first 1 or 2 neural networks, try to code your neural network, the calculating part and the optimization part by yourself. Then you will get a proper grasp of mathematics and get some feeling what is going on actually inside those neural networks. And also, if this is a mathematics talk, I will briefly touch on those. So, if you are trying to step into the AI field, these are the things that you need to learn very well before diving into the mathematics part of it. First thing is multivariate calculus that you start to learn in Method of Mathematics module in semester 2. I think there are something in the first semester now, I think under complex analysis as well. And you have to learn linear algebra. You can learn upcoming semesters. I know it is pretty much what you call boring module. Most of the guys are not like it because you have to do a lot of different things, but the key ideas are pretty much important. And then you need to understand the ideas of gradients pretty much well, the intuition behind the gradients, and you have to understand eigenvalues, eigenvectors, especially if you going to perform the dimensional reduction in your machine learning technique. If you learn this technique really well, you can compress your data into a very effective sense. It means you can get your outputs or inputs. You can, when you calculating your input, you can clearly figure out some pattern inside your data pretty much effective. And also you have to learn about optimization, convex and non-convex optimization, and also you have to understand how iterative algorithms works. If you trying to develop some algorithms that can train faster or train efficiently or some other thing. Because my final year research is based on these three ideas: idea of the gradients and optimization and iterative algorithm analysis. So if you can take out the form out of it and turn the data down, and you can Google inexact gradient descent if you like. You can see. That's Google it, right? And I think if you have internet, I can also do that, but it's better you can do that yourself. Inexact gradient descent. Inexact, exact gradient descent. Let's do that. Let's click it and go to the first result and see who's scored. It's still under peer review, but it's not published. But if you like, you can read about that paper. It is very heavy mathematical, but don't try to read it now. And if you don't understand anything, don't worry about it. I also took around, I think around 1 year to do that. Right? Still, there are some revisions coming, and I submit the second version. So you can think about that one, and you can do a lot of things. So imagine if you Google like that term and your preprint come at first, how are you feeling that? Because it is a very hot topic, and a lot of things we need to do in this area, but you need to learn these things. And because I not much going into pretty much high order mathematics in this case, because the first thing I need to give you the intuition is AI is not hard and AI is not magic, and the mathematics behind AI is pretty much simple. Because if I go into the very in-depth mathematics, and you will go straight and see what the hell is going on, and we can learn. The thing is, you can learn because you just finished your A-levels, you know what derivation is, differentiation is, you know what integration is, you know what vectors do. The only thing is, you need to start learning with more intuition. That's what I do before. Because if you see, very simple linear function can lead to approximate arbitrary complex function without this, without even mention. So the motivation of this talk is not giving you the theoretical background. Is like when you're going out to that thing, it's like give you about some degree on mathematics, all the mathematics bad there. The motivation of this talk is to motivate you guys to learn mathematics and tell you that it is not hard. It is pretty much straightforward. But the only thing is, people neglect those mathematics just because they think that they are pretty much complex, but it is not that complex. You can easily learn this. And also, I have some another news from my end, because I just show this to you, because I have some idea to initiate some theoretical research on this mathematical optimization area. So if someone in mathematical society or some of your friends if they are not there, they can inform them, and I will inform them we are the mathematical society if they agree to participate in that one. Because I think in Sri Lanka there are pretty much lacking research going on this theoretical aspect. So we need to start this somehow. I'm not a very big guy in that area either, but I think I have some experience I can share it with you, and probably you can do some better things than me in the future. Because I only have one preprint in the area, but if you are 22 guys start now, by the time you graduate you can have several number of publications under your name. So that's a very nice thing to have. So okay. So I talk a lot, I think, without a break. So now it's your turn to ask any question if you have. And sorry about that if I talk too fast, right? I told you before to give me some signal to slow down, and nobody has signal, and I feel that because I just planned to last this talk to little longer, but by the time I look at the clock, I see I go very fast actually, around 25% fast that I expect. Anything that you want I have to ask regarding machine learning? This guy showing some video. Any questions? Or anything like if you are, it can be regarding to memorization or anything. So your problem is why? Yeah. So the one question is like very. It is. I think you asked instead of neural networks, why use models, right? Okay. So first of all, I don't understand this. I roughly 5 years old there. So the thing is like this. Let's take an image, right? Let's go to the first slide, right? Let's say we go to the first slide. Let's say where's some here image. Okay, so the problem was why we use CNNs to perform this task. Okay, so now. See, if you want to learn the features inside this image, or you need to classify this image, you need to understand what is this contained in this image. So it is no point of executing linear layer on all of these pixels on the image. Because in images, what we need is actually, let's say if you use convolution, what it does is it is just consider only these three parts and take the linear of it and take some activation and to output to the next layer. So using convolution, what it learned is to identify some functions with respect to the neighboring pixels. That is enough to learn the features inside the image, the convolution operation. You can think of it that it means it is exposing the spatial features. It means if you take, let's say, 9 by 9 square, if you take here, it can exploit some of these, let's say it look like some ear or something. Because let's say if you need to, because if you figure out the cat, you need to figure out its eyes and its mouth and ears and so forth. So it means the whole picture doesn't contain the whole of the information, because these parts can be neglected. So using convolution filters, you can effectively extract those features to the specified images or segment. But when you come to the audio, the thing matter is, let's say when I'm talking now, let's say when I answer the question, you need to focus on the beginning of my answer, right? You don't need to focus like what I think on the hour before, to understand that context, to follow it. When you are understanding a sentence, you are reading a book, you need to focus on some sort of neighborhood, right? Let's say you are reading a 10th chapter, then you don't need to memorize the whole thing in the first chapter to understand those things. You need to memorize the content just before the text, or sometimes few pages before the text to understand the content, if the chapter is not finished. So in that case, like this thing we call sequential data, the things matter is the order of these things and what is the nearby thing. Let's say you are understanding, let's say you are listening to me, I'm speaking too fast, but sometimes you misheard one of my words. Then how will you correct it? You probably think what if I said just before that word, and you assume, okay, this guy should tell this word. Let's say I'm saying, let's say some dog, and you hear as is dog or something. But if I talk about animals before, you may say, oh, it is not about a dog, it should be a dog. So in that case, you need to have some features from the previous things or nearby things. So exploit that kind of thing. Recurrent neural networks, we have seen that it is doing better. So it is like not like that we don't have the computational power. It is like using the most appropriate architecture to our input data type. Because if you have time series data, you can go with recurrent type of network. But if it is image network, you can have to go with CNN network, because if you use fully connected networks, how many parameters you have? Let's say you have 100 by 100 image. You have 10,000 pixels, and if you consider all three channels, you have 30,000 pixels. And if you flatten them out and create a gigantic input, how many computations it will take? But in convolution, you can get away with, I think, around 27 parameters, because you have 3 by 3 convolution, you have 9, because 3 by 3 convolution means you have again block. It means 3 by 3 is a square, and you have 3 squares per each channel. So then you have 27 parameters. So using this kind of small amount of parameters, you can exploit many different features. So what will happen is, when you string to a network like this, you can perform many iterations in a shorter time, and then you can achieve high optimum. But if you use up lot of resources, and let's say you have 30,000 parameters, what will happen is, even to perform one iteration, you will take around 1 or 2 minutes. Then the number of iterations that you can perform will be less. So it is about like optimizing your performance. And also, my first job, I work at some US company which they are optimizing the machine learning models to run inside a custom hardware. So they are the lot of startups are there. I think you heard about analog inference, and also there's something called MTalks. They are all doing the same thing, and also there are several companies trying to do the same thing. And also NVIDIA is trying to do the same thing also. So what they are doing is, they take in the machine learning models and they try to figure out how to perform these multiplications and the non-linear arrays more effectively inside the computer. That's how CUDA comes in. In CUDA, if you get a graphical processing unit, the GPU, the processing cost is pretty much small. It only can perform a multiplication, addition, or some redo operation. It cannot perform a complex task that can have a normal CPU do. The power of GPUs coming in machine learning is, it has, let's say, sometimes it has 30,000 or 60,000 or even 1 lakh GPU processing units in one GPU. It means very simple units, but in large theory. It means, because in neural networks you only perform multiplications, additions, and those maximizations. It's a very simple task. So what you can do is make very little small cores that can perform that thing, and you can scale it up. So you can use 10,000 or 20,000 processors in one GPU. But you cannot have 10,000 CPU cores in one GPU, right? The maximum I think we have in commercially available, I think 16 or something. 16.2. Sri Lanka, I think it's around 16. So that's how you go. It is not about, we don't have computational power. It's about how we going to use this computational power. Are we going to burn up all of this for nothing, or can we do it in smart? So that's another question. So, and other things, so don't choose your field like, if I want to do AI, I want to go CSE, because in CSE you can do software development, because I'm not telling that I'm from electronic department, I'm telling this, don't go to CSE to do AI, right? But if you go to the machine electronic department, you will learn much about mathematical aspects. But there are two different parts, right? Because you need programming aspects in machine learning that we can learn from CSE, and the deployment stuff, more specifically in CSE, the main option kind of thing, industrial thing. And here you can learn about some kind of theoretical thing. So it is a kind of a trade-off. So depending on what path that you need to go on, you can choose them wisely. In each department, right? Even for the material or anything, it is not like I want to deal with materials, just for materials, not that case. So you need to understand what is actually provided inside those departments. So be wise. And if you have any sort of question like that, also you can ask. I think it's the first time I met you in person. I don't know if there is a horrible experience or not. What I say experience, I don't know. So any question? Maybe no question means there can be two things. One thing is you understand the picture, otherwise you understand nothing and still thinking about what just happened. Because it is, I think it's not much complex. The only thing I think if we I'm talking to you, then you can be off, right? It's really difficult. And if you want to learn this mathematics in detail, I think it is good to follow mathematics for machine learning specialization on Coursera. It's very good before you do any machine learning course, because it is just focused on mathematics. And then you can perform some of machine learning course like machine learning course by Endemic or deep learning specialization by Endemic. So that's one thing that you can do. Also, if you are interested in big data, there are also a lot of courses available to learn big data. But my advice is, don't forget the fundamentals. Because if you learn the fundamentals, then you will understand that although it had big names like AI, deep learning, or artificial intelligence or anything, but it will all of a sudden, like if you look at the building block, you will see that it is a very basic thing. So not a pretty much hard thing or not magic out there. So turn attention to those basics and learn the basics, and then you can be a good engineer in the future, and you can make a name yourself, and you can easily go through your university journey pretty much easily with stress free. Because I think the most prominent question I got from the juniors, like, I have this very stress. Some students take at midnight and say, I want to, my life is enough, I want to enjoy my life, and straight away they say, I want to do that. So in the midnight, sometimes I sleep, but I cannot sleep because next morning, if this guy has doing something in his life, I will also regret for all my life. So don't be in that way. Learn the subject, because every subject you learn in the mathematics courses or your software courses, there's something to deal with your future if you learn it correctly. Don't learn just for the exams. Don't do assignments just take for submissions. Just learn something out of it. It doesn't matter you get a B plus or A plus or anything. It doesn't matter the grade. The more important thing is how you understand this. If you tell me to teach multiplication calculus now, I can teach. It's no issue. If you give multiplication calculus paper now, you have the same paper, I will definitely score a pass grade. I don't say A plus because I have to revise that, but I can somehow pass. But if you learn in that way, that exams are out of your equation, and then you can do a pretty much good thing in the future, because then your amount of stress will be gone. Don't focus about GPA. In first semester, you should focus on GPA a bit, because that's what I do. Because in first semester, in my experience, I don't learn how to memorize those materials. I don't like, right? And also in fluid mechanics, I don't like, but what I do is like I learn them just for the exams and just pass it, and then once I come to the electronics department, I also not much learn about electronics pretty much well, because it is not my interest. I only interested in learn about signal processing and telecommunications and mathematics. Those are the key areas that I learn pretty much passionately, and other things I just learn for the exams. That's what I get A away. That's it. So if something goes wrong, I get A. So that's how my task is. You can have such classes like this. If you do it that way, you can properly manage your life. Don't try to do everything perfect just for your passion and do it correctly. Another thing, you can just take for the computer, because you just have to pass. Right? If I haven't passed electronics module, I still graduate of this department, and I still repeating those exams. So there are certain things in your world that you like to do and you have to do. So that there are kind of modules that you have to do and you like to do. So differentiate between those three and learn really well, and don't rely on the lectures itself, because lectures are to give you some sort of intuition or some sort of introduction to you. So more important is to learn by yourself. You have to focus on yourself, you have to self-study, you have to explore yourself and explore the subject yourself and gain the intuition. So lecturers are not there to teach you everything, they just are there to guide you. So that's one advice from me, because there are a lot of 22 guys and also 21 guys, and I think there are a little bit of 20 guys. So if you figure out in that way, if you learn on your own, by the end of 4 years, you can become a very good engineer and go out to the field. So same with go into machine learning or mathematics. Don't lose interest, just learn, and one point of time you will have to explore the sometimes pretty much interesting facts about those subjects, and sometimes you will realize that there's nothing but these are pretty much simple, and because when you learn it, you will understand that there are not much complex. At the same time, you will understand that there are a lot of things that you don't. I'm not saying at this point I learned all about machine learning or optimization, because there are a lot of things I don't. Still I learn. So be humble and help each other and do it that way. So if you have any questions, you can ask now. And be interactive, right? So don't like listen and go, because you are adults now. Because as an engineer, as a graduate, you need to have the guts to defend your opinion, right? When you go to the industry or you go to academia, you need to defend your opinion, because by the end of the time, by the way you finish degree, it is you end the time where you read a textbook and learn. After you graduate, it's all about creating theories and creating new things for the world, being some innovative. So if you want to do that, you need to be question yourself always. Even I tell something they are wrong, you should have the guts to say, "Hi, yeah, this is wrong," or "This might not be wrong." So don't be afraid. That's how science progresses, right? If we always worship Newtons and Einstein, we have no advancements. So keeping that in mind, because by the time you graduate, you need to have that skill as well. It means you have to be prepared. It means you don't have to be fear to stand up and ask a question or tell a different opinion. It's not too shy about. If you're smiling at someone, smiling at that kind of person is wrong in that person. Because that kind of thing, that's how we move forward. It's good for me as a talker or lecturer in a delivery session, and it's so good for you as well. Because if you're wrong, you learn something. If I'm wrong, or the speaker is wrong, or lecturer is wrong, he learns something. It's good for you. So that's one advice. So just take in mind, if you keep it that way, I think also this university will also improve as well. Because that's why give this advice to you. Because this is the place I learned also. And yeah. So any question you can ask now. I think only one question so far. There are a lot of boys nowadays 2025 and having no questions. I wonder, don't be shy. Right? If you are shy, you can just WhatsApp me. I turn on data on my phone and you can WhatsApp if you have questions. Anything? Or at least you have to add something or anything. If you get nothing, you can stand up and also score me. That's also fine. I shall turn on the data, but no message so far. So, anything? Okay, I think if there's no questions, I think we can end the session. I think organizers, they are how do we supposed to be? So if you have any question regarding machine learning or anything, also I will share the slides with you and the course. I will share through organizers. And if you have any additional question, you can always contact me. We have my mobile number, I think you have that. It's like public resource. So you can always call me or WhatsApp me. I will respond.
Thank you, Mr. Sandushan for that enlightening and captivating presentation. We have a small token of appreciation for you. To present that, I'd like to invite Samit Kavishkar, President of Mathematics Society, University of Malta.